Hello everyone, welcome to my YouTube channel. So in this lecture, I will teach about the Diels Alder reaction in the organic chemistry, which is very important reaction in the organic chemistry. So most organic reaction are ionic. Electrons move from one electron rich atom towards an electron poor atom. So anion or cations are the intermediate. So formation of electrons are as follows. So here plus protonation of this say carbonyl moiety, then nucleophilic attack of this oxygen from this oxygen lone pair, then 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 again protonation of the OH to from this OH equal to, and again nucleophilic attack, then this follows this lactone. So here the this reaction involves 5 steps and 4 intermediates. So this reaction is acid catalyzed and each intermediate is a cation. So electron flow in one direction in each step toward the positive charge. So this is a ionic reaction. So this is the classical many organic reaction follows this procedure. So there is a from electrons move from one electron rich atom to electron poor atom. So anions and cations are intermediate. So in the forthcoming part, we are going to consider the totally different type of reaction. Electron move around the periphery of a circle. There is no positive or negative charge on any intermediate. So indeed, there are no intermediate at all. This type reaction called the pericyclic reaction. So the most famous example of this class of reaction is the Diels Alder reaction. So the most famous example of Diels Alder reaction is the reaction that takes place on butadiene with malonic anhydride heated together at 100 degrees C. The product is obtained. So here the difference between this Diels Alder reaction and common organic reaction. Here this the electron flow between this the periphery of the circle of a molecule. There is no positive or negative charge on any intermediate. So this is the example on Diels Alder reaction. So on butadiene with react with malonic anhydride under thermal condition as a benzene solvent to form this final product. So this reaction goes in a single step simply on heating. So we can draw the mechanism with this electron going around this 6-membered ring. Each arrow reads the directly to the next, and the last arrow constitutes the first. So we have this drawn the electron rotating clockwise, but it would make no difference if we drawing the electron rotating anti-clockwise. So here the electron goes via this way, this double bond shifted this, and this double bond shifted this. So from this intermediate, it is a clockwise intermediate, and we can go via anti-clockwise intermediate. The same product is formed. So the strictly speaking, the electron do not really rotate at all. In reality, two pi bonds disappear and one sigma bond takes their place. The electron moving smoothly out of the pi orbital into the sigma orbital. Such rotation is called the cycloaddition. So in general terms, the reaction is one between the conjugated diene. It is a 4 pi electron system, and the compound containing a unsaturation, particularly alpha beta unsaturated carbonyl compound called the dienophile. The product of the Diels Alder reaction is often called an adduct. So this is the number example of the Diels Alder reaction. So here in the Diels Alder reaction, the two substrate, one called this diene, which is a 4 pi electron system, and another is the dienophile, which is a 2 pi electron system. So these two uh, substrate make a reacted together to form an adduct. So this is the classic example. This is the classic example of the Diels Alder reaction. So here this is the diene and this is the dienophile. So here is the adduct, and in this case, this cyclopentadiene is a acts as a diene, and this is a dienophile to form this adduct. And here this moiety acts as a diene, and this moiety as a dienophile. So it is a 4 pi electron, it is 2 pi electron to form this adduct. So in 1920, two German chemists Otto Diels and Kurt Elder developed the cycloaddition of a diene with a dienophile that has since come to the via their names. The reaction proved to be one of the such guest versatility synthetic utility that Diels Diels awarded the Nobel Prize in this 1950. So for this reaction, they got the Nobel Prize. So in the terminology, the orbital symmetric classification, so this reaction is a pi force plus pi 2 cycloaddition reaction, a thermally allowed process. So this is obvious from the interaction between the frontier orbital. So here the HOMO of this diene interact with this LUMO of this dienophile, that is a pi star. So here this orbital matching interaction, bonding interaction, and bonding interaction, or maybe the LUMO of this diene and HOMO of the dienophile, so that here also be the bonding interaction. So this is the interaction between the diene and dienophile from the orbital point of view. So next we will discuss how the Diels Alder reaction related in the number of important features. So the energetics. So in the Diels Alder reaction, two sigma bond and one pi bond are formed at the expense of two pi bonds of diene and one pi bond of dienophile. So since sigma bond are usually stronger than the pi bond, so formation of the adduct is usually favored energetically. So that is del H is negative. So this Alder reaction, two new sigma bonds formed and one pi bond is from the expense of two pi bond. So that means here this process is energetically favorable. So delta H is equal to negative. But the in the Diels Alder reaction, two moiety make a adduct. So here the entropically it is, but the Diels Alder reaction is entropically favorable. That is del S equal to minus V as the system is going to be ordered. Now you know that del S is negative. So here del G equal to del H minus T del S. That's the higher temperature. The Diels Alder reaction will follow reverse course. That is a butadiene synthesis by passing the cyclohexane vapor over heated nichrome alloy. So this is called a retro Diels Alder reaction. So here delta S is negative. So if the higher temperature, the retro Diels Alder reaction will proceed. So this is an example of the retro Diels Alder reaction. So next we will discuss as a normal and inverse electron demand. So in practice, the following reaction is unbearable slow. So it can be forced to take place 17 hours on 65 degree and 19 atoms. It does gives a yield 78%, but it is advisable for the dienophile to have a attached one or more electron withdrawing group like carbonyl, nitrile or nitrosulfonyl group. Thus, in this electron reaction with the malonic anhydride in the presence of two carbonyl groups allow the reaction take place even in the 20 degree C for 24 hours. However, the reaction is carried out at 100 degrees C in benzene medium to give quantitatively yield. So here, when normal cyclobutadiene 1,3-butadiene and the ethylene moiety reacts, this reaction is very much slow. But when this 1,3-butadiene reacts with this malonic anhydride, where electron withdrawing this carbonyl group is present, so that case the reaction is facile even at the lower temperature. So electron withdrawing group has a role in this reaction. So let us consider the following example. Here also these three reaction. When this reaction at 150 degree and 10 hour got 80% yield. When one electron withdrawing group, the aldehyde group is present, the reaction goes in a 6 hour. And when these two ester group are present electron withdrawing, that reaction goes as even at 25 degrees C. So here we can see that the select electron withdrawing substituent on this dinophile make this reaction more feasible. So thus, if you look at the different dinophile, the dimerization of the butadiene is slower than is the reaction with the acrolein. Similarly, we found that any alkene with two electron withdrawing groups like methylene malonate, so it is very much reactive. So an acetylenic ketone is a little more reactive than the ethylenic counterpart. So substitution on the diene also, so that means electron withdrawing substitution on the dinophile will increase the rate of this reaction, and also the substitution on the diene also increase the rate provide which is provide electron withdrawing donating substituted like methyl alkoxyol amino group. Looking at the effect of changing the structure of the dienes, we found that electron donating substituted on C1 and C2 even as the weak as the methyl group in. So here electron donating group in the C1 position and C2 position will increase the electron donating increase rate of the reaction. The methyl group on the piperylene and isoprene makes this diene more reactive than the butadiene. So here electron donating substitution on C1 position make this reaction facile at more facile at 6 hours. When isoprene case also the reaction goes at 130 degrees for 6 hours, and when the methoxy group that is more electron donating than the methyl, in that case the reaction even goes at lower temperature at 2 hours, so it is more reactive compared to this. But here in this case, when is 1,3 cyclopentadiene, there is no electron donating substitute. That case the reaction goes is 20 degrees 60 hours. So methoxy group on the diene part is still more reactive. Again, most impressive is the cyclic dienes are the most reactive than the open diene. So in the first three example, there is the possibility of the formation of both the regioisomer. We are consulting considering only the major ones. So from this study, it is clear this dinophile of type electron withdrawing substituent group on the electron withdrawing group and the diene having the electron donating substituted are the better substrate for the decellular reaction. So that means electron donating substituted diene and electron withdrawing substituted dinophile will make this decellular reaction more facile manner, better candidate for this decellular reaction. So the simplest explanation for how the substitution effect affect the rate is what is the relative energy of the frontal orbital. So it is electron donating substituent. So it electron donating substituent, jet substituent lower the energy of the LUMO of the dinophile, and the electron donating substituent X substituent raise the energy of the HOMO of the diene, and the smaller of the energy gap faster the reaction. So that means obviously the estimate energy for level of HOMO of X substituted diene we have considered energy level of the two ideal system. So here this HOMO of the butadiene and the HOMO of the pentadiene anion. So here the HOMO of this pentadiene anion is slightly upper in energy compared to this HOMO of the butadiene. So now the energy level of the HOMO of the X substituted diene will come between the corresponding energy levels for above 2 extreme percent. As a result, it is clear that the energy level HOMO of the X substituted diene is higher than of the simple butadiene. So similarly, the estimated the energy level of the LUMO of the Z substituted alkene, the dinophile, we have considered the energy level of the LUMO of two ideal system, ethylene and allyl carbocation. So here LUMO of the ethylene and the LUMO of the allyl carbocation. So a LUMO of the ethylene molecule is higher energy compared to the LUMO of the allyl carbocation. So now the energy of the LUMO of the Z substituted alkene, the dinophile will the one come between the corresponding energy level for the above two extreme version. As a result, it is clear that the energy level of the LUMO of the social alkene is lower than the simple ethylene. So now this is the example. Here the for interaction of the butadiene with this simple alkene. So when this is the homo and this is the LUMO, so homo-LUMO interaction. This is homo or LUMO. So when the substitution on the dienophil, when the LUMO energy of the LUMO is decreased. So that means here the energy gap is decreased. So that time the in electron within substituted dienophil will reacted with more faster rate. And also when the X substitute electron substitute diene, so that case the homo is some slightly raised and LUMO is slightly lower. So that case also the energy gap is lower. So obviously from this above we can say that the energy separation between homo of the butadiene and the LUMO of the jet substituted dienophile is less than the between the homo of the butadiene and LUMO of the ethylene. Similarly, the energy separation between the homo of a X substituted diene and the LUMO of the jet substituted dienophile is even smaller. The reaction is faster still. So this is the reason why the substitution will favor the reaction. So to be a good dienophile in the normal disorder reaction, the most important factor is the low lying LUMO. Thus, the electron more the electron withdrawing group we have on the double bond, the lower the energy of the LUMO, and the smaller separation of homodiene and the LUMO dienophile, and faster the reaction. So that means for a good to be a good candidate in the disorder reaction, the electron withdrawing substitution on this um, dienophile, more the electron withdrawing substitution in dienophile, that will be more the reaction rate will be more higher for this dienophile. So again, Lewis acids such as a chloride, aluminum chloride, or diethyl aluminum chloride catalyze the Diels-Alder reaction. So catalytic effect is resulted from the coordinator of the Lewis acid with the dienophile, thereby the energy of the LUMO of the dienophile is decreased. So this is the example where this diene reacts with the dienophile. So from this adduct to possibility. So here when this in absence of this any Lewis acid, the reaction occurs 120 degrees C for 6 hours. So in presence of the Lewis acid AlCl3, the reaction goes to 20 degrees C for 3 hours. So here the in presence of Lewis acid, the reaction is more, reaction rate is very much higher. So this is the because the in the presence of the Lewis acid, the LUMO of this dienophil is slightly energy is decreased, so energy gap between the HOMO of the diene and the LUMO of the dienophile is decreased. So that's why the reaction is most faster. So it is also possible, but usually less effective, to increase the rate of the Diels-Alder reaction by having the electron donating X groups on the dienophile, raising the energy of HOMO, and electron withdrawing substitute on the diene, lowering the energy of LUMO. So these Diels-Alder reactions describe the second place with the inverse electron demand, but this is less effective to carry out the Diels-Alder reaction with this inverse electron demand. It is not obvious why. So, but adjusting the energies of the HOMO and LUMO of the both and diene and dienophile, we can set up the reaction to achieve both normal and inverse electron demand of the same system. For example, this tetraphenyl cyclone and substitute styrene to from this Diels-Alder adduct. So this is the diene, this is the dienophile, and this is the diene. When electron withdrawing substituted on this para position, that case the rate is higher compared to the normal. And also the electron donating substitution, when this para position, that case also the reaction rate is higher. So it is found that the tetraphenyl cyclone reacts with the unsubstituted styrene slower than with the substituted styrene, whether the substituted electron donating or the electron withdrawing. So energies of the HOMO and the LUMO of this diene are eventually so split with respect to the system. When R is H, neither HOMO-LUMO interaction is much stronger than the other. When R is a electron withdrawing substitution, LUMO of the diene lower and bringing it close to the energy of HOMO of the diene. When R is electron donating substitution, the HOMO of the dienophyne is raised and the bringing is close to the energy of the LUMO of the diene. So here that means the electron donating substitution or electron withdrawing substitution on this dienophyne molecule will um, lower down the energy gap between this the homolumo in homolumo of this diene and dienophyte. So that's so why the for both electron donating and donating substitution the rate is higher. Now we will discuss about the S-cis configuration of the diene. So diene are necessity must react with the S-cis configuration rather than the S-trans. So diene has two conformation. One is the S-cis, this is the S-cis, and another is S-trans. So in the Diels Alder reaction, the S-cis conformation is required for this Diels Alder reaction. So that's why the S-cis in the S-trans configuration, two ends are higher in distance. Again, if the reaction proceed via S-trans conformation, as then we'll get a cyclohexene derived with the trans double bond, which is highly strained system, thus are impossible to attain. Cyclic diene in which the double bond are held, the S-cis configuration is usually highly reactive than the Diels Alder reaction. Cyclopentadiene, for example, reacts with the malonic at room temperature to give this Diels Alder reaction. So that's why the closed diene is react very faster than the open diene, because the cyclic diene, the closed diene, that means the cyclic diene, they are in the always in the cis configuration, so that's why they are more reactive compared to the open. So cyclopentadiene also reactive than on the standing and the room temperature, is solely undergo Diels Alder reaction with itself. So cyclopentadiene even react with itself to form this Diels Alder adductora. So this reaction is reversible. However, when the dicyclopentadiene is distilled, it follows the reverse course that dissociate into two molar equivalent cyclopentadiene. So again, in the another approach, Diels Alder reaction have the large negative entropies of the activation, particularly for the acyclic dienes, reflecting not only the loss of the translation energy when the two molecules come together, but also the high degree of ordering, which is corresponding to the mutual orientation of four atomic centers. Thus, the comparatively high temperature necessary to carry out the dicyclic Diels Alder reaction in the acyclic diene in the comparison to the cyclic dienes. So next factor is the steric effects. So the Diels Alder reaction are the sensitive to the steric effect of the two major types. So bulky substitute on the dienophile or the terminal of the diene can hinder the approach of the two components to each other and decrease the rate of the reaction. So here, so in this diene substituted with this electron, here the steric bulk will increase the reaction rate with the malonic anhydride will decrease with increase the steric valve. So when R equal to CH3, the slight increase in the rate of the reaction due to the electron withdrawing releasing effect of the methyl group, but when R equal to tert-butyl group, the steric effect is dominated. So other type of the steric effect arise due to the interaction between the diene substitution during the adaptation of the S configuration. Thus, when the R equal to H and CH3. So here, when R equal to CH3, there is a steric interaction between this H and the CH2 group. So that will discover the in the cis configuration. So that case, the election rate is very much low. So this is because of the unfavorable interaction between the additional methyl substitution C1 and hydrogen in the cis configuration. Obviously, this substitute will try to remain in the S-trans configuration. That's why the rate is very much low for this CH2 group. So relatively small substitution on C2 and C3 of the diene extract little steric influence on the rate of the Diels Alder reaction. So when R dash CH3, the rate is slightly increased, and when this tert-butyl and hydrogen rate is slightly increased. So that means the electrons with the donor That means the substitution effect, the static effect on the substitution of the C1 position is the most prominent compared to the C2 and C3. So when R equal to CH3, R dash equal to CH, the rate of the reaction is unchanged due to the electron releasing effect of the methyl group, but the when R equal to R butyl and HS configuration of the diene is more stable, there is the S turn configuration. So that's why here when tert-butyl, the S cis configuration is the more stable than the S trans due to the sterically. So that's why the reaction rate is much higher even on the steric more bulky tert-butyl group. Thus, here the rate of the reaction increase largely. Next, we will discuss about the stereoselectivity of this Diels Alder reaction. So the Diels Alder reaction occur in one step to so that that neither the diene or dienophile has time to rotate. This must have to approach in the parallel planes. Thus, the stereochemistry of each must be faithfully reproduced in the product. And thus, we have the following observation. So here, this diene reacts this dienophile. Here, two phenyl group are in cis position. So here these two ester group in this in trans, here also this in the product these two ester group in the trans position. So here the stereochemistry of so this means plus the stereochemistry of each must be faithfully reproduced in this product. So again with properly substituted dienes, the dienophile another problem will arise, the endo versus exo addition. This is obvious from the following example. So here in this endo addition, this product is formed. In this exo addition, this product is formed. So in the endo addition, the reference of the substitution of the dienophile is oriented towards the pi orbital of the diene. In the exo addition, the reference substitution of the dienophile is oriented away from the diene. This problem is easy to see in the cyclic system as. So here this cyclopentadiene reacts with the cyclic dienophile in the endo addition. So here this is towards the ring. So from this product, and here when it is to the exo addition, it is away from the ring to from this product. So now one of the most challenging stereochemical finding in the Elder's endo rule for the Diels Alder reaction. So endo addition is associated with the favorable transition state, but through the addition of the electron withdrawing substituent on the dienophile is more hindered environment and the diene unit. Thus, the endoadact formation is continually more favorable, but the thermodynamic is less favorable, and heating eventually equates these two adducts in favor of to the exoadact, which is less steric conjunction by the retrocyclization followed by the re-addition pathway. So that means the endo addition product is the kinetically favored product, and the exo addition product is the thermodynamically favored product. So when the endo addition product is formed, that case the favorable interaction will happen, and that's why it's fast kinetically stable product. But when hitting the reaction, that will form this exo product. So here these two molecules react when this lower temperature, we got the endo addition product, and we increase the temperature, in that case we got exo addition product. So in the reference, substitution on the dienophile is oriented away from the pi orbital of the diene, and in the endo product, the references substituting on the dienophile is oriented towards the pi orbital of the diene. So thus endo addition is kinetically controlled and the exo addition is a thermodynamically controlled. So the lower temperature will favor the exo addition and the higher temperature will follow exo addition. So any reaction in which the kinetic effect overrides the usual thermodynamic effect on the reaction rate in immediately interesting the demand in the explanation. Thus it can be explained as, so in Diels Alder reaction, two pi bonds and two sigma bond and one pi bond are formed at the expense of pi, two pi bonds so of the diene and one pi bond of the dienophile. So since sigma bond is usually stronger than the pi bond, so formation of the dienophile the Diels Alder reaction is usually favored energetically, del H is negative, but the Diels Alder reaction is entropically unfavorable, that is del S is negative. So the reaction, the system is going to be ordered. So now we know that del G equal to del G is H minus T del S, thus due to this high temperature, the Diels Alder reaction will follow reverse course. So in this Alder reaction, the endo product is more sterically congested than the exo product. Thus, exo product is more stable than this endo product. So again, endo addition is associated with the lower energy of activation because of the attractive type of secondary bonding interaction between the dienophile substitution and the pi electron of the diene. So if you place this orbital in the appropriate place of the endo reaction, we see that there is a usually primary interaction with the overlap of the orbital with the matching phase consistent within the rule, but there is an additional bonding interaction between this other lobe. This secondary orbital extent does not lead to a bond, but it might made a contribution to the lowering the energy of this transition structure relative to the exotic reaction, this where it is absent. So this obvious that the following diagram, homo of the diene and lumo of the dienophile taking cyclopentadiene as a standard substrate. So here this is the homo of the dienophile cyclodiene and the lumo of the cyclopentadiene. So here when it is goes via this endo addition product, here this type of secondary interaction, and this is the primary bond forming interaction. So due to this secondary orbital interaction, the reaction which contribute the lower the energy of the transition state, that's why the endo addition product is a more favored compared to the exo addition product. So again we may consider the following figure with the Diels Alder reaction is between the cyclopentadiene and the malonyl anhydride. This is the endo product, this is the exo product. So in the endo product, this primary interaction happen, this this secondary interaction happen, this this but for the exo product only this primary interaction happen, no secondary interaction is happen. So that case this endo is favored compared to this exo addition product. So again the malonic anhydride and the furan give the exo product even at the lower temperature. This is because although the endo product is formed about the 500 times faster than the exo product, it reverts to reactant about the 100,000 times faster. Thus the exo product is more favored. So from this summary, till now, so from first one the electron donating substitution on the diene and electron withdrawing substitution on the dienophile will give more reactive to the Diels Alder reaction. Second one, the electron substitution on the C1 position of the diene will disfavor the Diels Alder reaction due to the steric effect, and in the Diels Alder reaction, endo product is a kinetically controlled product and exo product is the thermodynamically controlled product. Due to this, in the endo product, there is a primary and secondary orbital interaction, but in case of the exo product, there is a only the primary interaction product. So that's why in the lower temperature, in the Diels Alder reaction, the endo product is formed, but in case of a higher temperature, the exo product is formed in the Diels Alder reaction. And also in the in case of stereoselectivity, in the Diels Alder reaction, the stereochemistry of each molecule is reproduced in the product. So thank you everyone.